Alright, I'm back. Sorry for the delay. We're starting up video 2. We are going to start off with problem 15.4. Problem 15.4, electrified oil. Tiny droplets of oil acquire a small negative charge while dropping through a vacuum. In an experiment, an electric field of magnitude 5.92 times 10 to the 4 newtons per coulomb points straight downward. One particular droplet is observed to remain suspended against gravity. The mass of the droplet is 2.93 times 10 to the minus 15 kilograms. Unimaginably small mass. Find the charge carried by the droplet. And then in part B, another droplet of the same mass is going to fall a distance, 10.3 centimeters, and it's going to do that in a quarter of a second, and we need to find the charge on that droplet. So, part A. 15.4. We were told that we had an electric field with a strength of negative 5.92 times 10 to the 4 newtons per coulomb, negative because the field's going in the downward direction. The mass of the droplet is 2.93 times 10 to the negative 15 kilograms. And we are trying to find the charge on that droplet. So, free body diagram. So there's Q naught. We are feeling a force upwards, Coulomb force, and a force downward, a gravitational force. The droplet is suspended, which means it's just hovering there, so we are not accelerating. We know that net force equals ma. In this case, we know we have a Coulomb force and a gravitational force, and they add up to 0 because we're not accelerating. The Coulomb force is Q naught E, and that's going to equal the gravitational force, which is mg. So Q naught will equal mg over E. And when we plug in all those numbers, we end up with negative 4.85 times 10 to the minus 19 coulombs. That charge is negative, which means a whole bunch of extra electrons on it. Cool. That was part A. Part B. So that was part A. Part B. Part B says another droplet is of the same mass is going to fall 10.3 centimeters from rest in a quarter of a second. Find the charge carried by that droplet. So part B. We have a displacement of negative 0.103 meters. We're dropping. We have an initial velocity of 0. We're starting from rest. We're going to take an amount of time equal to a quarter of a second. We are trying to find the charge on that droplet. So here we have our droplet. There's Q naught. We have a Coulomb force upwards from the field, and we have a gravitational force downwards from the gravitational field. We are now accelerating some amount because we're going from rest, moving at that rate, and we need to figure out the charge. Well, like before, net force equals ma. We have a Coulomb force and a gravitational force, and now that equals ma because we're not equaling 0. Problem is, unlike in the last problem where there was no acceleration, this time there is, and we don't know it. If we know that acceleration, we can use it to finish the problem. So let's figure out the acceleration. Well, that goes all the way back to our kinematics, and I don't know if you guys remember the kinematic equations, but this would be equation 3 that we would like to use today. Solve that for A, and we get negative 3.3 meters per second squared. So we know V naught is 0, we know the time is a quarter of a second, and the acceleration is what we're trying to calculate, and the displacement we knew was 0.103 meters. So we get our acceleration. Awesome. All right. Once we have our acceleration, we can go back and say, well, force of that minus force of that equals ma. So Q naught E minus mg equals ma. Solve for Q naught. And when we do that, we get negative 3.22 times 10 to the minus 19 coulombs. Cool. So that was example 15.4. Moving on. Example 15.5. A little bit more vector decomposition stuff. So charge Q1, 7 microcoulombs, 7 times 10 to the minus 6 coulombs is at the origin, and charge Q2, negative 5 times 10 to the minus 6 coulombs is on the x-axis, 0.3 meters from the origin. Find the magnitude and direction of the electric field at point P, which has coordinates given there. So it's on the y-axis, 0.4 meters up. All right, so diagram something like this. We have a positive charge here. Let me draw that differently. We have Q1 here, and it's positive. We have Q2 here, and it's negative. And that distance is 0.3 meters. We have up here point P. And I'm going to already know that I've messed this up, and I'm going to give myself way more room. There we go. There's point P. And it is a distance 0.4 meters away. And we'd know, because we know about 3, 4, 5 triangles, that that must be 0.5 meters. All right, and we're trying to find the electric field strength right here from these two charges. What do we know? Well, we know that Q1 is 7 times 10 to the minus 6 coulombs. Q2 is negative 5 times 10 to the minus 6 coulombs. Okay. So how do we do this? Well, charge 1 is going to produce a field. That'll be the electric field from charge 1. Charge 2 produces an electric field. Charge 2 is negative, so the direction of that field would be towards charge 2. So that would be field E2, that way. And just as a little reminder, that's an angle, and we will say that that angle is 53 degrees. Why is that 53 degrees? Well, that's just how 3, 4, 5 triangles work. So let's find E1 and E2, and when we combine them, we will figure out E. Okay? Oh, and I'll remind you of something else here. That's also theta. That's going to be helpful for us to know. All right, cool. So E1 equals K Q1 over R squared, which equals, R is this one, because we're talking about Q1, that's R is this one, and Q1 is this. So that gives us a value of 3.93 times 10 to the 5 newtons per coulomb. Calculate E2. That's going to be KQ there, so we're going to have, that's R. So we have KQ2 over R squared. So that's R in this case for E2. That's Q2, which is this value. When we do all of that, we end up with a magnitude of 1.8 times 10 to the 5 newtons per coulomb. I said magnitude because the direction is going to be this direction. It's going to be the direction right towards, so it's going to be at the direction of that angle. All right, to combine these two vectors, that vector and that vector, this vector and this vector, we're going to do vector decomposition. So E1x equals 0. E1y equals 3.93 times 10 to the 5 newtons per coulomb. E1 has all y component and E1 has no x component. E2x equals E2 cosine theta, which equals, when I calculated it, 1.08 times 10 to the 5 newtons per coulomb. E2x, that's E2 right there, so the x component would be this, and this is adjacent to my angle, which happens to be my 53-degree angle. And when we calculate that, we get this value here. E2y is going to be E2 times the sine of that same angle, and that's going to be negative 1.44 times 10 to the 5 newtons per coulomb. So we have E2 is this, so E2x is that vector, E2y is this vector. E2y is negative because it's that way. It's in the negative direction. So EX is going to be E1x plus E2x. EY is going to be E1y plus E2y. So E will equal EX squared plus EY squared, all square rooted. And when I calculated that, I came up with 2.71 times 10 to the 5 newtons per coulomb. And the direction for this is the inverse tangent of the y component over the x component. And when we calculate that, I came up with 66.6 degrees. And to show you on the picture, that is phi. That is the angle we just calculated, the angle for the electric field E. We did it. That is part A. We're almost done, folks. Part B. Part B says find the force on a charge of 2 times 10 to the minus 8 coulombs placed at P. So 2 times 10 to the minus 8 coulombs, and we know that F equals Q naught E. We know E and we know Q naught, so we can calculate F. So we got E, Q naught, and we can calculate F. And if we do that, we come up with, learn to write, 5.42 times 10 to the minus 3 newtons. That is that for the problems. You guys should work on the 2 exercises. That was problems 15.4 and 15.5, so you should do exercises 4 and 5, and we'll call it. We'll see you live next time.